Hello, Mr. Ryan.
Hello. I got a robot.
Okay. Okay, so we given agreed, right? Agreed. You know the chess, right? Maybe chess.
Doing a nice tool.
Yes, chess. Okay. We given agreed with number of rows. We know the rows and columns.
That's not square though.
Okay, so now just imagine we have a knight.
Why knight?
The horse, right? The horse. So we place the horse knight on the grid, one of the grid. You know how we travel, how the knight travels?
Yeah, like L.
The air, right? Yeah, the air shape. So this place. How many next possible positions? I just draw it, right? How many of those?
8.
8. The number of possible moves is 8. You know, if it does not cross the boundary. We know the start position. Okay? And we want to find out the path, if there's a path, possible path that the knight travels each position exactly once. So we want to find out, we want to put the numbers on the grid as it travels. So let's take a look at this. Simple example, okay? This is too big. Consider a simple example. Why the pen is just rubbish? Ryan, okay, this is better. Okay, so maybe here, right, at the beginning, the position we put a 0. Okay, so the next one, imagine if I put a 1 here, 2 here, 3 here, 4 here, 5 here, 6, 7, 8, 9, 10, 11. Okay, I can't go back, right? Because this has been visited. Do you see my point, right? So we want to find out.
Where do we start?
Sorry?
Where do we start?
Given the start position, C. Okay. So this is not the right way. This is 4 times 4. Okay. How about let's take a
2 by 2.
4 times 3. Okay. Here. Take a look at this example. So if we start here, maybe 0, 1, 2, 3, 4, 5.
You can't go anywhere.
6. Okay. So yeah, we need to find out the example that.
Can I try?
Yeah, maybe.
Let's all just try.
Yeah, let's just try.
Shall we try 4 times 4?
Yeah, and I
Oh my
need to.
god, this pen is just...
Yeah, I know. Just find.
This
There's
pen.
a pen. There's a more.
This pen is quite good. That pen is quite rubbish. If I'm starting
You
here...
can use this one, right, Eric? Eric? Maybe this one.
Okay, doesn't matter. Okay, so
This one, yes.
the 0, 1.
Okay, you understand the problem anyway, right?
1.
Yes, yes.
So it will either be here, 1. No, I'll just write 1, 2, 3.
Well, okay, so you have 1. It's a difficult
5.
question, right?
I found 5. This is all I can do. This is all I can do.
Yeah, I know. So this
I made 5. I made 14.
Okay, maybe we try 3 times. Is it possible with a 3 times 3? 1, 2, 3, 4. No, 3 times 3 never, right? 2 times 2, 2 times 3. No. So the smallest we can do, I think, is 4 times 3. 4, 3, or 3, 4.
I'm pretty sure 4 times 4 is possible.
Okay, maybe
No.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh no way. Okay, so let's look at this.
Is it just leaving out 1?
No.
Flashing light robots.
Highly. 3 columns, 4 rows. 3 columns, 4 rows. So it starts with the first position. Start with the first position. Okay. 4 rows, 3 columns. So here, 1, 2, 2 zeros, Okay, 0, 1, 0, 1. Yeah,
And then 1, 3.
here. 1, 3 here. And then
It says 2, 1. And then 0, 2.
0, 2.
2, 3. 1, 1.
Aha, okay, look. Okay?
Yeah.
Okay, so this is the example, right? 3 rows, 4 columns. 3 rows, 4 columns. So we start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Each position is visited only once. Okay, and then we put the numbers as the order the knight visited. We put a number as the order, the sequence that the knight travels.
Yes.
So, okay, as we can see, this is not an easy question. It's not easy to find it, right? So, how can we use the algorithm? Which algorithm can we use to traverse the grid using this air shape? You know the air shape, right? So, if we travel from A, B to C, D, okay, so we travel A, B to C, D. So the distance A minus C, the minimum A minus C, and B minus D. This the minimum is 1. The maximum of these is 2, right? Okay, so air shape, there are 8 positions. How do we try? What would you? Yeah, depth search. The backtracking, right?
Yes.
So I mean, how do we try usually? If we start here, how do we try? So given this grid, how do we try? Okay, so here we know this is 0. So how do we try? Right?
Why?
Yeah, how many next positions can we try? In this particular case,
2.
2, yes. We can try here and we'll try here. Okay, we're not sure, right? Let's take this one here, 1. And how can we try?
We have.
We can't try here, right? Because it's already visited, alright?
Yes.
Yeah.
1.
We can try here, or we can try, that's the only position, we can try here. Okay, and then same, here, we can try here. Here, we can go back. We can try here, or we can try here, okay? If I try here, if I try here, and I can keep going until we don't have valid moves, alright? Yes?
Yeah.
So until what's the target?
Visit all of them.
All of them. Which number? The last number. Look, this is
You
3.
can't visit that one if you do it like that.
Yeah. Okay. So look, there are 3 rows, 4 columns. What's the last number that we target to put on the grid?
12.
We start with 0.
11.
11. Yes, we know that, right? So we know the target, right? So as long as we bypass the last number, which is 11, if we are trying to fill in the 12, which means that we already completed. Okay? So yes, if not, I can just retract and try other position, right? So for example, like I know this 4, I'm filling this 4, but it turns out if I put the 4 here, I don't find a solution. What does it mean? It means that I don't put a 4 here, I can try put a 4 here. Right? I put a 4 here and I found a solution somehow. Right? Make sense? So look, if I try here 4 here and I keep trying, I can't find a solution by putting a 4 here. It means that this is not a correct solution. I can put a 4. Am I right?
You could then do 5, 6, 7, 8, 9,
And 10.
10.
And what's the last number? 11.
11's here.
Oh yeah, 11, yes. Okay?
Yeah.
Okay, so depth search, backtracking. Okay, so we put in the number because there are at most 8 possible moves. We can try each of them as the next move. And if we find a solution, that's great, we find a solution. If not, then we backtrack and try the next one. The tree will be like that. It's a search tree, right? At the beginning, start here at 0, right? In theory, there are 8 possible solutions, right? Those are all the ones, right? Air shape, remember air shape. Maximum 8. I pick one of them, right? I can, if I can go to the next number, I keep going until I reach the one, and then that's great. If not, it means that we can't find a solution. It means that this one, we can't put a 1 here. So we can put a 1 in the next position. And then we try searching. Am I right? Does it make sense? Yeah. Each one has at most 8 possible kids, right? So it's eighth. It's not a binary tree. It's a, what do you call a tree which has at most 8 kids?
N tree.
8. What do you call it? Code? No.
Isn't it
Oh.
tree? N tree.
Binary tree.
Octatree.
Octatree. Yes, octatree.
That just sounds weird.
Octree, okay? Because oct means 8, octree. So it's an octree. Each node has at most 8 kids, meaning that there are possible maximum 8 next moves, right? Because in an air shape, right? This is the knight. It has 8 possible next moves. We pick one of them. We try each of these next kids by turn until we find it. Make sense?
Yes.
Okay, there's something we need to pay attention when we do the coding. Is that if we don't find it, we have to put the number back. How do we find out if a cell has been visited? How do we find out if we have already visited a cell?
We just put it down like numbers.
Set.
And,
We do a notepad counter.
okay, put a number. Yes, but,
You just put a number down.
so my question is, how do you distinguish between a cell has been visited and not visited?
You
It's
just
a number.
you just put something there.
At the beginning, what do we put? At the beginning, what do you put?
Number.
What number?
0.
0 means the first one. Okay, so what are those numbers? At the beginning, they are not visited. We can put any numbers. What numbers?
You can just put 0, 1, 2, 3, 4.
We put the numbers, but these number, what's these number?
Is empty cells.
Empty cell. Okay, so if we want to use a number to represent the empty cell, what would you pick? What's the range of the numbers we put in this grid? If there are 16 cells,
We could put a 5 there.
what's the range of the numbers that we
You're
put?
not like wording the question
Okay,
correctly.
so what are the
I
numbers?
understand.
Yeah, okay, let me repeat. What is the number range? What's the number range that we put finally on this grid? If there are 16 cells.
0 to 15.
Well done. 0 to 15, okay? So these 0s to 15, those are the numbers that are valid, right? So what are the numbers that we can use? You know, it could be anything. You mean something, right? What is the number we can use to distinguish from the numbers we have visited?
100.
Well done, 100. Yes, as long as it's not in the range, right? As long as it's not in the range, we can put minus, next minus 1, minus infinity. That's what I'm saying.
Infinity is no number.
Make sense, yes?
Infinity is no number.
Or is it because my wording is not correct?
Probably because your wording is...
Okay, so how would you describe it? You now understand my intention, right? So how would you describe it?
With that,
Yeah. So how would you, for example, like your daddy, how would you describe to Eric and Ryan that, I want to know which number, right? So any number not in this range, because this range means the number has been visited. You can put 100, a million, as long as it's not in this range. It's a special number that we know it's not visited, am I right? Because at the beginning we're not visiting the cell. We have to use a special number to know. We have to use a special number to mark it not visited. Am I right? Yes.
Yes.
Okay. Define backtracking. Okay. Backtracking is type of depth search. Backtracking. We're given a grid. We're given a star position, star row, star column. We want to return an answer, right? Which is the complete solution, a board. Okay. At the beginning, let's use minus 1, right? Minus 1 means we haven't visited. Times the columns for underscore in range rows. Okay. So this is meaning that we have a grid which is the minus 1, contains minus 1. Every cell is minus 1 because we haven't visited, right? For number of columns, this is columns, this is rows, okay? And then we use the backtracking depth search. Depth search, we currently add rows and columns. And then we are currently filling the step n. This is the number we want to fill, the third parameter, okay? Current position, current row, current column, and the position, and the numbers we want to fill. If this n, right, is already the 12, right? If we already reaching the n, so if n equals the number of rows and columns, okay, so the rows and columns here, rows and columns is the size of the grid, okay, so rows equals the length of grid, columns equals the length of the grid 0. We want to get the dimension of the rows and columns of the grid.
Okay.
Actually, do we need to pass in the grid? No, right? Because we can just pass the grid here. Rows, we just want to know the rows and columns. We don't need to know we don't need to pass the original grid. Rows and columns. So if n equals the rows times columns, then we return true. We're reaching the end, we return true. Otherwise, there are 8 possible next positions, right? So what are the offsets for the rows and columns? So it will be 1, 2, 1, minus 2, minus 1, 2, minus 1, minus 2, 2, 1, 2, minus 1, minus 2, minus 1, minus 2, how many of those? 2, 1, 2, 1, 2, minus 1, minus 2, 1, and minus 2, minus 1, okay? So this D is the offset of the next possible positions. So we can just add the offsets of the rows and columns, then we get the positions of the next one. For example, like 1, 2. What's 1, 2? 1, 2, if we are here, right? 1, 2 means that we're adding the 1 to the rows, adding 2 to the columns. So it's this one, right? What's 2, 1? 2, 1 means that
Moving
2 here and then 1 here, right? You get it, eh? So there are 8. 1, 2, there are 8. Why there are 9 here?
Maybe you wrote 1 twice.
1, 2, 1 minus 2, minus 1, 2, minus 1 minus.
Are they the same?
Yeah, okay. For dr, dc in d, and then next position would be nr equals dr plus r, right? nc equals dc plus c. But obviously this could cross the bound. It could be out of the range, right? So we need to check. If nr bigger than equal than 0, smaller than rows, and nc bigger than equal than 0 or smaller than columns, and answer, okay? Save the answer. We haven't visited the number, right? We haven't visited the position nr and c. It's not equal minus 1, right? This is the number minus 1. Because at the beginning we put the minus 1. And we travel it, right? We can travel it. If DFS, RNR, and C, we use the n plus 1 because the next number we want to fill is n plus 1, right? Yes? Okay? Then we return true. Right? But before that, we need to mark the current number, which is the IS NR and C equals R. And after, right, if we don't find a solution, we need to unset it to minus 1. Make sense? Okay, and return false at the end here. Here, false. Okay, so depth first search at the beginning, the RC, the first number we want to fill in is 0. Okay, and then we return the answer.
Yes.
Because we don't know which one is the next, right? Okay? We don't know which one is next, but that's fine. The computer is very good at doing this trying thing. Yeah? Okay, so we are at the beginning, we are at this position 0, okay? So there are a few next moves. As a human, we don't know which one leads to a solution, right? But that's okay, we ask computer to try each of them. This one is possible next move, this one is possible next move. Okay, let's put a 1 here. And we keep trying. Look, we put a number 1, the next number we put a number 2, right? Until we put the last number, we return true. Okay, so these are the 8 next moves, the offsets. These are the offsets for the next moves. And we try, okay, so this is the next move location. If the NRNC, if the next position is still in the range, still in the ball, and it's not being visited, it's still minus 1. It can't be the number we have put before, right? Yes? Okay? Yeah, we find such number, then we set it to n, right? We put down the number, and then we try the next number, n plus 1, with this location, am I right? Yes? And if it returns true, then we simply return true here, okay? Okay, so look, why we need to set it to -1, right? Look, let's take this one, right? But it turns out that with this one, we can't find a solution. So there's another one that we can try here. We can put a 1 here, right? Yeah? What happened to this one? We have to mark it to...
-1.
Yes, why if we don't mark it to -1, what happened?
Then you want to visit it.
That's right, and we can't find a solution. Brilliant. We ask computer to try put a 1 here. And if we put a 1, the computer can't find the solution. So, okay, the computer then backtrack and say, okay, let's try to put a 1 here. Okay, so by the previous one, we have to unmark it to make it -1 so we can visit it again. That's what they mean here. Yeah, we set it number to n. We visit we try to depth search with the next number n+1, and then if we don't find it, we need to mark it as -1. So basically, this is depth search on an occ tree. Occ tree is
I'm not sure if it's called an occ tree. I don't think it's called an occ tree.
okay. So
Sounds
n
weird.
Or octo tree.
octo tree. Okay, it's basically a tree
It
with
should be
at
called
most 8 kids. If n is 2, if a tree has at most 2 kids, each node in the tree has at most 2 kids. What do we call it?
Binary tree.
Very down, binary tree. Okay, and if it has at most 8 kids, we call it. We don't know. Okay,
How about an n-ary tree?
n-ary tree. N could be anything. Okay, n could be bigger than 2. How about n? If n is 1, what happened? What do we call it?
Line.
If n is 1, n-ary tree. If n is 1, what happened?
Binary.
N is 1. N is 2 is binary.
Tree.
Unary tree. We just call it a.
Unary tree.
It's not a tree. I
Line.
mean, yeah, it's a tree. We can call it a unary tree, or we can call it a linked list. Right? A linked list. It's a linked list. It's a chain. It's a linked list. It can be seen as a unary tree. Okay. The time complexity. Right. This is too difficult. The time complexity because
O-N.
no. No, it's not OM because we try at this position. We need to try a possible position, right? So it will be
Again.
a to the power of
Squared. 2.
a position. Look at this tree, another tree, right? Right? You have a kids. This is the a kids, and for each a kid, you still have roughly a kids, right? So how many of those, right? So n a to the power of n. N is the numbers we put there. Okay, this is the upper bound. Okay, look, it's exponential. Make sense? Just consider if it's a binary tree. Just consider if it's a binary tree. It's a binary tree. Each position you can have 2 next kids. So it's 2 to the power of n. Right? And look, if it's a kids, right? Because the tree has at most 8 kids, then it's a to the power of n. Okay, that's it for today. Bye bye.
Bye.
Bye bye. Bye bye. Bye bye. Bye bye.
Bye 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 bye.
Mine did not happen.